There is a quiet question that has followed thinking creatures for as long as there have been creatures capable of asking it. It shows up late at night, in the pause between one thought and the next, and it never quite resolves. The question is simply this: what is the relationship between the mind that is doing the wondering and the universe that is being wondered about? Most of the time we do not notice the question at all. We go about our days assuming, without ever quite deciding to assume it, that the world is simply out there, solid and settled, and that our minds are small, private theaters somewhere off to the side, watching the show. But the moment you sit with that assumption for more than a few minutes, it starts to feel less obvious than it first seemed. Tonight is a good time to sit with it, gently, without any pressure to arrive at an answer. We are going to spend some time with one of the oldest and strangest ideas in the history of human thought. The notion that mind, in some form, might not be a late arrival in the universe's story, but something closer to its foundation. It is an idea that has gone by many names across many centuries, and it has attracted serious attention from philosophers, physicists, and neuroscientists, alongside a great deal of speculation that goes well beyond what anyone can currently demonstrate. Our aim tonight is not to convince you that the universe is a mind, or that it is not. It is to walk slowly through where these ideas came from, what a small number of serious researchers actually argue today, where the evidence stands, and where careful thinking gives way to something closer to hope or intuition. Some of what follows rests on solid, testable science. Some of it rests on centuries of philosophy that remains genuinely unresolved. And a little of it, as we will see, turns out to be less ancient than it appears, dressed up in old language to sound wiser than it is. Telling these three categories apart is most of the interesting work. Let us begin the way any patient explanation should begin, with the thing that makes the whole question difficult in the first place. That thing is consciousness itself, the simple, undeniable fact that there is something it is like to be you right now, listening to these words rather than nothing at all. Consciousness is a strange word to define because everyone already knows what it means from the inside, and almost no one can explain what it means from the outside. You know, without any doubt, that you are having an experience right now. There is a quality to hearing a voice, a quality to the dim light in the room, a quality to the particular tiredness or calm you might be feeling. Philosophers have a technical word for these qualities. They call them qualia, the raw felt textures of experience, the redness of red, the specific ache of missing someone, the taste of something sweet before you have even named it. You cannot hand someone your qualia. You can describe them, gesture toward them with metaphors, but the actual first-person feel of being you seems to resist being translated into anything else. This creates what the philosopher David Chalmers named the hard problem of consciousness in the 1990s, a phrase that has stuck because it names something real. There are plenty of what Chalmers called the easy problems of consciousness. Easy only by comparison, things like explaining how the brain processes visual information, how it integrates sound and sight, how it stores memories, how it reports on its own internal states. These are hard in the ordinary scientific sense, requiring careful experiments and years of work, but they are the kind of problem science already knows how to attack. You can imagine, in principle, a complete map of every neuron firing in a brain as it recognizes a face, and that map would explain the mechanism. The hard problem is different. Even with that complete map in hand, a further question remains open. Why should any of that electrical and chemical activity be accompanied by an inner experience at all? Why isn't all that information processing simply happening in the dark, with no one home, the way it presumably happens inside a thermostat or a calculator? There is, as far as anyone has been able to demonstrate, No logical contradiction in imagining a being that behaves exactly like a conscious person, that flinches from pain, that reports feeling happy, that writes poetry about heartbreak, and yet has no inner experience whatsoever, no felt quality to any of it. Philosophers call this hypothetical being a philosophical zombie. Almost no one believes such zombies actually exist among us, but the fact that we can coherently imagine one at all is itself revealing. It suggests that a complete physical description of a brain's behavior does not, by itself, obviously entail that there is something it is like to be that brain. Somewhere between behavior and experience, there is an explanatory gap, and nobody has yet built a bridge across it that satisfies everyone. This gap is not a fringe concern. It sits at the center of serious philosophy of mind and increasingly at the center of serious neuroscience. Because it turns out that even our best theories of the brain do not, on their own, tell us why there is experience rather than none. A theory can tell you which brain regions light up when someone sees the color red. It has a harder time telling you why that lighting up feels like anything. Why it is not simply information moving through wires the way it moves through the circuits of a phone. Faced with this genuine puzzle, thinkers across history have taken several very different routes. Some have simply denied that the puzzle is as deep as it looks, arguing that consciousness will eventually be explained away as a kind of user illusion generated by the brain. A story it tells about itself that feels real without being fundamentally different from ordinary information processing. This view, associated with philosophers such as Daniel Dennett, is called illusionism, and it has its own committed defenders, though many find it unsatisfying precisely because the experience of redness does not feel like an illusion from the inside. Whatever else it might be, others have gone the opposite direction, suggesting that if physical description alone cannot explain experience, then experience must be doing something that pure physics, as currently understood, does not capture. Some of these thinkers propose that mind and matter are two fundamentally different kinds of thing, an old position called dualism. Others propose something stranger and, in recent decades, increasingly discussed in serious academic philosophy, that experience, in some very minimal form, might not be something that only shows up once matter becomes sufficiently complicated, the way it seems to when a brain grows sophisticated enough to support thought. Instead, perhaps some trace of experience, some faint spark of interiority, is present all the way down, in every interacting piece of matter in the universe. And what we call human consciousness is simply what happens when billions of these tiny sparks are woven together into something rich and unified. This is the idea usually called panpsychism, from the Greek roots for all and soul or mind. And it is the idea we are going to spend the bulk of tonight exploring, along with several of its cousins and several ideas that get mistaken for it. Before we get to the modern arguments, though, it is worth taking the slow route back through history, because almost nothing about this question is actually new. Human beings have been circling it for thousands of years, and the shape of the argument keeps rhyming with itself across very different eras, cultures, and vocabularies. The earliest Greek philosophers we have record of, writing in the centuries before Socrates, were already asking what the world is fundamentally made of, and several of them gave answers that sound surprisingly close to panpsychism. The Lees of Miletus, generally regarded as the first person in the Western tradition to try to explain nature without appealing directly to the gods, is reported to have said that all things are full of gods, or in some translations, that the magnet has a soul because it can move iron. Whatever exactly Thales meant by this, later writers took it as evidence that he attributed something like life or mind quite broadly to matter, not only to living things in the narrow sense. His younger contemporaries continued down similar paths, proposing that the underlying stuff of the cosmos, whether it was water, air, an undefined, boundless substance, or fire, was itself somehow alive or intelligent, actively organizing itself into the ordered world we observe rather than being pushed around by something external to it. It is worth pausing on how differently these early thinkers saw the relationship between mind and matter, compared to how many people instinctively see it today. In much of contemporary thought, especially outside philosophy departments, there is a default assumption that matter comes first, dead and mindless, and that mind arrives late, as a strange and almost accidental byproduct of certain complicated arrangements of that matter, namely brains. This assumption is sometimes called physicalism, and it is the working assumption of most of modern science, for good reason, since it has been extraordinarily successful at explaining an enormous range of phenomena. But it was not the default assumption of the ancient world, and it is not obviously forced on us by anything physics itself says. Physics describes the behavior of matter with remarkable precision. It has, at least so far, remained conspicuously silent on the question of whether that matter has any inner life while it behaves that way. The philosopher who most shaped how later Western thought would frame the relationship between mind, matter, and a deeper reality was Plato, working in Athens in the early 4th century before the Common Era. Plato is not usually classified as a panpsychist in the modern technical sense, but his metaphysics set up a way of thinking about the relationship between appearance and reality that echoes through nearly everything that came after, including the modern arguments we will get to shortly. Plato proposed that the physical world we perceive with our senses, the world of trees and tables and human bodies, is not the most fundamental level of reality. Instead, he argued, every physical object is an imperfect, changing copy of a perfect, unchanging form or idea that exists in a separate, non-physical realm. A particular chair you are sitting on, worn and specific and eventually destined to break down, is an imperfect echo of the form of chairness itself, an eternal template that never wears out and never changes. The same goes for more abstract things. Every just act in the world is an imperfect echo of the form of justice. Every beautiful thing is an imperfect echo of the form of beauty. Mathematical objects, Plato thought, are the clearest example of all, since a perfect circle or a perfect triangle exists nowhere in the physical world, and yet mathematicians reason about them with total precision and universal agreement, as though they were studying something real rather than making it up. Plato illustrated the gap between appearance and reality with what has become one of the most famous images in the history of philosophy, the allegory of the cave, found in his dialogue called The Republic. He asks us to imagine prisoners chained in a cave since childhood, facing a blank wall, unable to turn their heads. Behind them burns a fire, and between the fire and the prisoners, unseen puppeteers carry cut-out figures whose shadows dance on the wall in front of the prisoners. Having never seen anything else, the prisoners take the shadows to be the whole of reality. They give the shadows names, argue about their movements, perhaps even develop something like a science of predicting which shadow will appear next. Now imagine, Plato continues, that one prisoner is freed and dragged, painfully and reluctantly, out of the cave into the sunlight above. At first the light is unbearable. Slowly his eyes adjust, and he begins to see the real objects that had only ever cast shadows before. And eventually the sun itself, the source of all the light by which anything can be seen at all. If this freed prisoner then returns to the cave to tell the others what he has seen, Plato suggests he will not be believed, and may even be mocked or resented for disturbing their comfortable certainty. The allegory works on several levels at once, and Plato clearly meant it as commentary on education, on the fate of philosophers who challenge popular opinion, and on the structure of reality itself. For our purposes tonight, the most relevant layer is the last one. Plato is proposing that ordinary sensory experience, however convincing it feels, might be something closer to shadows on a wall, a flickering, secondary representation of a deeper and more stable reality that our senses cannot directly access, but that our minds, through careful reasoning, might be able to glimpse. This is a significant move, because it treats the physical world we can touch and measure as somehow less fundamental than an underlying structure that is closer to thought than to matter. The forms, in Plato's system, are not physical objects sitting somewhere in space. They are more like perfect ideas, apprehended by reason rather than by the senses. In this sense, Plato's universe has something like a mental or rational structure underneath its physical appearances, even though he was not proposing that individual rocks or rivers have private inner experiences, the way modern panpsychists suggest. Later thinkers, particularly in the Neoplatonic tradition that developed a few centuries after Plato, pushed this idea further, describing reality as emanating outward from a single, unified, mind-like source, with the physical world as one of its outermost and least perfect expressions. Plato also touched on a related puzzle that still occupies philosophers and cognitive scientists today: the question of where our knowledge of abstract, perfect things like mathematical truths could possibly come from, if we have only ever encountered imperfect physical approximations of them. His answer, laid out in dialogues like the Meno, was a theory of recollection, the idea that the soul existed before birth, in direct contact with the forms, and that learning is really a process of remembering what the soul already knew before it became attached to a body. Few philosophers today accept this literal story of pre-existing souls, but the underlying puzzle it was trying to solve has not gone away. It resurfaces, dressed in new clothes, in a famous 1960 essay by the physicist Eugene Wigner, who wrote about what he called the unreasonable effectiveness of mathematics in the natural sciences. Wigner was struck by how often a piece of mathematics developed by mathematicians purely for its internal elegance, with no thought of physical application, later turned out to describe some previously undiscovered feature of the physical world with startling precision. Why should abstract patterns invented in the human mind map so exactly onto the deep structure of the universe? It is, in a sense, Plato's old question wearing a lab coat, and it remains genuinely open, discussed by physicists and philosophers of mathematics without full agreement to this day. Skipping forward almost 2,000 years, past the medieval synthesis of Greek philosophy with Christian, Jewish, and Islamic theology, we arrive at a thinker who gave the question of mind and universe one of its most rigorous and controversial treatments. The 17th century philosopher Baruch Spinoza, working in Amsterdam and later in The Hague. Spinoza was raised within the Portuguese, Jewish community of Amsterdam and was formally excommunicated from that community at the age of 23. In an unusually severe ban whose exact reasons were never fully recorded, though his philosophical writings, only fully known later, give a strong sense of why his ideas were considered dangerous. Spinoza ground lenses for a living, a detail that sometimes gets romanticized, but that placed him, quite literally, in daily contact with the emerging science of optics that was reshaping how Europeans understood light and vision. His major philosophical work, called simply The Ethics, was written in the geometric style of a mathematical proof, moving from definitions and axioms through propositions and demonstrations, as though the nature of reality and of good and bad could be derived with the same rigor as a theorem in geometry. It was published only after his death in 1677, partly out of fear of the reception it would receive. At the heart of the Ethics is a claim that shocked many of Spinoza's contemporaries and still strikes many readers today as radical. Spinoza argued that there is only one substance in the entire universe, one fundamental thing that exists in itself and is conceived through itself, and that this single substance is what people call God and what people call nature, understood as one and the same thing. He wrote the phrase Deus sive natura, God or nature, treating the two words as interchangeable names for a single, infinite, necessary, self-caused reality. Everything that exists on this view, from planets to thoughts to human beings, is not created by God as something separate from God, the way a carpenter is separate from a chair. Instead, everything that exists is a particular expression, or as Spinoza called it, a mode of this one underlying substance. The way a wave is not separate from the ocean, but is a particular temporary shape the ocean happens to take. This view is often called substance monism, from the idea that reality is fundamentally one substance rather than two or many, and it is also a form of what later thinkers would call pantheism, identifying God with the totality of nature rather than picturing God as a separate, personal being who intervenes from outside. Crucially for our purposes tonight, Spinoza's single substance has, according to him, infinitely many attributes, though human minds can only perceive two of them, thought and extension. Extension is roughly what we would call physical, spatial being, the property that makes something occupy space and have shape. Thought is mental being, the property of thinking, perceiving, and willing. Spinoza's radical claim is that these two attributes, thought and extension, are not two different substances interacting with each other, the way Descartes had proposed a few decades earlier with his famous division between mind and body. Instead, thought and extension are two different ways of describing the exact same underlying reality. The way you might describe a single event in the language of chemistry or in the language of physics without those descriptions referring to two different events. Every physical thing, for Spinoza, therefore has a corresponding mental aspect, not because a soul has been added to it from outside, but because thought is simply one of the two ways that all of reality can be truthfully described. This is not identical to modern panpsychism, and Spinoza's scholars debate exactly how literally to read his claims about the mental aspect of ordinary physical objects, but the family resemblance is clear enough that Spinoza is regularly cited as an important historical ancestor of panpsychism thought. His famous line, quoted widely and referenced even in casual conversation about determinism, holds that nothing in the universe is contingent, but all things are conditioned to exist and to act in a particular way by the necessity of the divine nature. For Spinoza, the universe unfolds with the same kind of logical necessity that governs a mathematical proof. There is no room, on his account, for events to have happened otherwise than they did, and there is no external, willful deity choosing outcomes moment to moment. There is only the single, necessary, self-unfolding whole, which we can look at through the window of matter or through the window of mind, and which we call, depending on our mood and our vocabulary, either nature or God. Spinoza's ideas were considered dangerously heretical by many of his contemporaries, and he was largely written off as an atheist in disguise for over a century after his death, since identifying God with nature seemed, to many religious readers, functionally the same as denying God's existence altogether. But his reputation slowly recovered, and by the time of the German Romantic movement in the late 18th and early 19th centuries, Spinoza had become a celebrated figure among poets and philosophers who were drawn to the idea of a universe suffused with a single underlying, quasi-divine unity, one that did not require a personal, judging deity, but that still inspired a sense of awe and reverence toward the natural world as a whole. This reverent, non-personal conception of nature as divine had a famous and unusually direct influence on 20th century physics through the person of Albert Einstein. In 1929, a rabbi in New York sent Einstein a telegram asking bluntly whether he believed in God, and Einstein's reply, quoted ever since, was that he believed in Spinoza's God, who reveals himself in the lawful harmony of what exists, not in a God who concerns himself with the fates and actions of human beings. Einstein returned to this theme repeatedly throughout his life, describing his sense of cosmic religious feeling as a deep, wordless conviction that the universe is rational and harmonious at its foundation, a feeling he distinguished carefully from belief in a personal deity who answers prayers or rewards virtue. He described this feeling as the strongest and noblest motive for scientific work, a sense of awe at the comprehensibility of the universe that he considered close to what more conventionally religious people might call a religious experience, even though he explicitly rejected the anthropomorphic elements of traditional religion. It is worth being precise here, since Einstein's religious views are frequently misquoted in both directions, sometimes to claim him as a conventional believer, and sometimes to claim him as a straightforward atheist. Neither framing captures what he actually said with reasonable consistency over several decades. Einstein's God was not a being who could be prayed to or who intervened in history. It was something closer to Spinoza's identification of God with the rationale, orderly, comprehensible structure of the universe itself, and a structure whose very existence, whose sheer intelligibility to a mind trying to understand it, struck Einstein as the deepest mystery worth wondering about. This is a genuinely different position from panpsychism, as philosophers use the term today, since it is a claim about the universe's rational order rather than a claim about tiny sparks of subjective experience distributed through matter. But it belongs in this history because it shows how persistently serious scientific minds have felt that there is something more than pure mechanism sitting beneath the equations, even while remaining committed, as Einstein was, to methodological rigor and skepticism toward claims that could not be tested. To understand why panpsychism faded from serious discussion for a long stretch of modern history, and why it has recently come back, it helps to look briefly at the philosopher Spinoza was reacting against. His older contemporary, René Descartes, writing earlier in the 17th century, proposed a much sharper division between mind and matter than Spinoza was comfortable with. In Descartes' system, there are two fundamentally distinct kinds of substance in the universe: thinking substance, which has no extension in space and is the seat of consciousness, and extended substance, which occupies space, has size and shape and motion, and includes everything physical, including, crucially, the human body and brain, along with the bodies of every animal. For Descartes, animals were essentially complex machines, capable of behavior but not, in his view, capable of genuine inner experience. Since experience required an immaterial thinking substance that only humans possessed, this view is called substance dualism, and it created what philosophers still call the mind-body problem. Since Descartes now had to explain how a non-physical, unextended thinking substance could possibly interact with a physical, extended body, a puzzle he never fully solved, despite proposing, somewhat awkwardly, that the interaction happened through a small structure in the brain called the pineal gland. Descartes' dualism dominated much of European philosophy for generations, but it left behind an uncomfortable puzzle that later thinkers spent centuries trying to escape. If mind and matter are truly two different kinds of substance, how can a physical event, like a pinprick, cause a mental event, like the sensation of pain? And how can a mental event, like a decision, cause a physical event, like a hand moving. The interaction problem, as it came to be called, pushed later philosophers in several different directions. Some, like Spinoza, resolved it by denying that mind and matter were truly separate substances in the first place, treating them instead as two aspects of one thing. Others moved toward materialism, denying that there was a genuinely separate mental substance at all, and arguing that mental events simply are physical events, described from a different angle, or perhaps are nothing more than the behavior and dispositions of a physical system. A view called behaviorism that dominated psychology for much of the early and middle 20th century, as the natural sciences achieved their extraordinary successes across the 18th, 19th, and 20th centuries, explaining chemistry in terms of physics, biology increasingly in terms of chemistry, and eventually much of psychology in terms of neuroscience. Physicalism became the working default of most working scientists and a great many philosophers. On this view, consciousness, whatever it turns out to be, must ultimately be explicable in terms of physical processes in the brain. Full stop, without needing to posit any additional non-physical ingredient. This remains the majority position in philosophy of mind today, and for good reason. Since physicalist assumptions have guided an enormous amount of successful neuroscience, but the hard problem of consciousness, described earlier, never quite went away under physicalism, and by the final decades of the 20th century, a number of serious philosophers had become dissatisfied with every available option. Substance dualism seemed to revive Descartes' old interaction problem. Strict physicalism seemed, to its critics, to leave the very existence of subjective experience unexplained, no matter how detailed the physical description became. Illusionism, denying that experience is what it seems to be, struck many as changing the subject rather than answering the original question. It was in this context that a small but increasingly influential group of philosophers began to take a fresh, more careful look at panpsychism, no longer as a piece of ancient or mystical speculation, but as a serious logical option worth examining on its own terms. One of the most important figures in this revival has been the British philosopher Galen Strawson, whose provocatively titled paper from 2006, called Realistic Monism: Why Physicalism Entails Panpsychism, argued that physicalists, if they are being fully consistent about what physicalism actually commits them to, are already closer to panpsychism than most of them realize. Strawson's argument runs roughly as follows. We know, with more certainty than we know almost anything else, that experience exists. Since your own experience right now is the one thing you cannot coherently doubt, if physicalism is true, and everything that exists is physical, then experience itself must be physical, must be a genuine feature of the physical world, not an illusion layered on top of it or an extra ingredient added to it from outside. But, Strawson argues, our standard picture of matter as fundamentally inert, mindless stuff, arranged in complicated patterns that somehow, at some threshold of complexity, gives rise to entirely new experiential properties out of nothing, is deeply mysterious in a way that ordinary physical emergence is not. When water molecules come together to produce liquidity, we can trace, in principle, exactly how the properties of the parts explain the property of the whole. Nobody has offered a comparably clear account of how non-experiential particles, arranged in a brain, could give rise to something as different in kind as felt experience. Strawson concludes that the more parsimonious option is to suppose that matter, even at its most basic level, has some form of experiential or proto-experiential character built in from the start, and that what we call consciousness in complex systems like brains is what this basic experiential character looks like once it becomes richly organized and integrated. This argument does not claim that individual electrons are thinking about their day. The experience being attributed to fundamental particles, in this view, is imagined as something vastly simpler and more minimal than human consciousness, perhaps nothing more than the barest, most rudimentary flicker of felt quality, utterly unlike the rich, narratively structured experience of a human mind. The philosopher Philip Goff, another prominent contemporary defender of panpsychism and the author of several books aimed at general audiences, has described this basic form of experience using an analogy to physical properties like mass or charge, fundamental features that every particle has to some degree, without those particles doing anything remotely like what large-scale objects made of many particles can do. A single water molecule is not wet, Goff points out. Even though wetness is a genuine property of water, once enough molecules come together in the right way. Perhaps, he suggests, something similar is true of experience, present at the most basic level in an unimaginably simple form, and only becoming what we would recognize as consciousness once matter is organized into something as intricate as a nervous system. This modern, carefully argued panpsychism is a genuinely different creature from ancient animism or from popular New Age. Claims that crystals or planets have thoughts and feelings the way a person does. Its defenders are explicit that they are not attributing anything like human-style thoughts, memories, plans, or emotions to fundamental particles. They are making a narrower metaphysical claim about the presence of some minimal experiential ingredient throughout matter, motivated by a specific argument about the difficulty of explaining how experience could emerge from something entirely without it. Even so, panpsychism in this modern academic form faces a serious, widely discussed difficulty of its own, usually called the combination problem. If a single fundamental particle has some tiny flicker of basic experience, how do billions of these tiny separate flickers combine into the single, unified experience of a person? The felt sense that there is one experiencer having a coherent, integrated conscious life, rather than billions of unconnected micro-experiences happening side by side without ever merging into anything. Critics of panpsychism argue that this combination problem is at least as hard as the original problem panpsychism was invented to solve, since it is not obvious how you get from many tiny separate subjects of experience to one larger subject of experience, any more than it is obvious how you get from mindless matter to any experience at all. Panpsychists have proposed various responses, some suggesting that combination happens through certain kinds of causal integration among physical systems, others suggesting that we should think of the situation the other way around, with a more fundamental, unified cosmic experience somehow giving rise to the seemingly separate experiences of individual creatures, a view sometimes called cosmopsych. None of these responses has achieved anything like consensus, and the combination problem remains, by the admission of panpsychism's own proponents, one of the significant open difficulties the view has yet to resolve. It is worth holding on to that honestly, since it is exactly the kind of unresolved technical difficulty that separates a live philosophical research program from a settled conclusion. With that philosophical background in place, we can turn to the first of the more recent, more technical arguments that sometimes get invoked in support of panpsychism, an argument that actually began as an attempt to solve a very practical and pressing medical problem rather than as a piece of speculative metaphysics. The neuroscientist Giulio Tononi, working first at the University of Wisconsin and drawing on decades of earlier collaborative work with the neuroscientist Gerald Edelman, was trying to solve a genuinely difficult clinical puzzle. Doctors treating patients with severe brain injuries, patients in comas, in vegetative states, or in what is now called unresponsive wakefulness syndrome, badly needed some objective way to determine whether a given patient retained any capacity for conscious experience. Since a patient who is conscious but unable to move or speak, a condition called locked-in syndrome, can be easily and tragically mistaken for a patient who has no awareness at all. Behavioral tests, which rely on a patient's ability to respond to commands, are useless for telling apart a mind that is present but unable to act from a mind that is genuinely absent. Tononi's response to this problem was to try to define consciousness not by its behavioral signs but by its intrinsic structural properties, asking what any conscious system, whatever it is made of, must have in common. He proposed that consciousness requires two things simultaneously. First, it requires differentiation, meaning the system must be capable of an enormous number of distinct possible states, since a rich conscious experience carries an enormous amount of specific information, distinguishing this exact moment from an astronomical number of other possible moments it could have been but is not. Second, it requires integration, meaning that this information must be unified, experienced as one single, coherent scene, rather than as separate, disconnected fragments. When you look at a red apple, you do not experience the redness, the roundness, and the appleness as three separate, unconnected experiences happening in parallel. You experience one unified perception of a red, round apple. From these two requirements, differentiation and integration, Tononi developed what he called integrated information theory, generally abbreviated as IT, first proposed in 2004 and substantially revised in later versions, with the most developed version usually referred to as IIT 4.0. The theory proposes a formal mathematical measure, denoted with the Greek letter phi, that quantifies how much integrated information a physical system generates, based entirely on the system's own internal causal structure, meaning how its parts influence each other, rather than on what the system does from the outside. Any system with a phi value greater than 0, according to the theory, possesses some degree of consciousness, and the theory further proposes that the particular quality or character of a given conscious experience corresponds to the particular shape of the system's integrated causal structure, described in the theory's more technical writings as a structure in an abstract space called qualia space. This is a genuinely bold theoretical move, because it does not restrict consciousness to brains or even to biological systems. It restricts consciousness only to systems that have the right kind of internal causal organization, meaning high integration together with high differentiation. Tononi and his collaborators have been explicit and consistent that this has strange-sounding implications. A brain's cerebral cortex, they argue, likely has a high phi value and is therefore strongly conscious, which fits the everyday intuition that this is where human awareness lives. The cerebellum, a part of the brain with roughly as many individual neurons as the cerebral cortex, but organized in a much more modular, less interconnected way, likely has a very low phi value on this theory, despite containing a comparable number of neurons, which is consistent with clinical observations that patients who lose most of their cerebellum while suffering serious motor difficulties generally do not report any corresponding loss of conscious awareness. This match between the theory's prediction and an independent clinical observation is often cited by the theory's supporters as a point in its favor. But the theory's implications extend well beyond brains, and this is where it connects most directly to panpsychism, because phi is defined purely in terms of a system's internal causal structure. In principle, any physical system with the right kind of interconnected structure could have a non-zero phi value, including, at least hypothetically, sufficiently interconnected non-biological systems. And, at the furthest and most speculative extreme, the universe considered as a whole, understood as an enormously complex, causally interconnected system integrating information on a cosmic scale. Tonon himself has generally been cautious about pushing this cosmic extension very far in his formal, published work, focusing his own research primarily on biological systems and clinical applications. But other writers and some of his collaborators have been more willing to explore the panpsychist adjacent implications of the theory in public writing. And it is genuinely true that integrated information theory, taken to its logical conclusion, does not rule out some degree of consciousness in systems well outside the biological world, provided they have a sufficiently integrated causal structure. This is one of the main reasons integrated information theory keeps coming up in discussions of panpsychism, even though it began its life as a working theory in clinical neuroscience rather than as a philosophical argument about the ultimate nature of matter. The theory has produced one genuinely useful, practically tested clinical tool, developed by Tononi's close collaborator, the Italian neuroscientist Marcello Massimini and colleagues. In 2013, this research group introduced what they called the Perturbational Complexity Index, a measure designed to translate the theoretical insight of integrated information theory into something that could actually be measured at a hospital bedside. The method works by using a technique called transcranial magnetic stimulation to deliver a brief, painless magnetic pulse directly to a patient's cortex, while recording the resulting pattern of electrical activity across the scalp with a brain that is capable of consciousness, the theory predicts, should respond to this simple pulse with a complex, widespread differentiated pattern of activity that unfolds across many brain regions and many points in time, because a conscious brain is by hypothesis richly integrated and richly differentiated. A brain that has lost the capacity for consciousness, by contrast, whether through deep anesthesia, dreamless sleep, or severe injury, tends to respond to the same pulse with either a very simple, localized pattern that does not spread, or with a pattern that spreads widely but in a stereotyped, repetitive way that lacks genuine differentiation. The Perturbational Complexity Index compresses the recorded response using an algorithm and produces a single number that reliably across large groups of patients, states known independently to involve consciousness, such as ordinary wakefulness, from states known independently to lack it, such as deep anesthesia or dreamless sleep, and it has since been used, with encouraging results published in multiple peer-reviewed studies, to help identify covert consciousness in some patients diagnosed as unresponsive by behavioral criteria alone. This clinical tool stands on its own scientific footing today, tested and used in real hospitals. Regardless of how the broader philosophical debate about integrated information, theory's more speculative, panpsychist implications eventually settles, that broader debate, it should be said plainly, has become genuinely heated within the scientific community in recent years, and it is worth reporting honestly rather than glossing over. Integrated information theory has long been controversial among consciousness researchers, admired by some as the most mathematically rigorous framework in the field, and criticized by others as making claims that are difficult or impossible to test. One particularly sharp early critique came from the computer scientist Scott Aronson, who pointed out in published commentary that the theory's mathematics, taken literally, implies that certain extremely simple systems, such as a large grid of interconnected logic gates arranged in a particular repetitive pattern, could in principle be assigned an enormous phi value, larger than that of an actual human brain, despite doing nothing that resembles thinking, perceiving, or behaving intelligently in any way. Aronson argued that this counts as a serious problem for the theory, since it suggests that high integrated information, as currently defined, can be produced by systems that share no other resemblance to conscious beings, which raises doubts about whether phi is really tracking consciousness at all, as opposed to tracking some other structural property that happens to be present in brains but is not unique to them. This kind of technical criticism escalated sharply in September of 2023, when a group of 124 consciousness researchers, including a number of prominent figures in the field, published an open letter arguing that integrated information theory, as it currently stands, should be publicly labeled pseudoscience, on the grounds that important parts of the theory as a whole are not empirically testable, and that some of its proponents had, in the signatories' view, overstated the strength of existing supporting evidence in public communication. This letter caused what several science journalists covering the story accurately described as an uproar within the consciousness research community. A number of other well-regarded researchers in the same field, including some who had themselves published criticisms of the theory's specific claims, publicly objected to the letter's use of the word pseudoscience, arguing that a theory can be wrong or difficult to test with current methods without meeting the more specific and serious definition of pseudoscience, and that applying that particular label risked discouraging legitimate research into a genuinely difficult scientific question rather than sharpening it. A subsequent anonymous survey of researchers who had published on theories of consciousness found only a small minority fully agreeing with the pseudoscience characterization, with most respondents falling somewhere in between full agreement and full disagreement, suggesting a field that remains split rather than settled on the question. Perhaps the most informative recent development came from an unusually rigorous scientific effort, specifically designed to move past exactly this kind of dispute. Starting several years earlier, a large international research group called the Cogitate Consortium organized what is known as an adversarial collaboration, a format of scientific inquiry in which researchers who hold opposing theoretical positions agree in advance on a specific experiment, on exactly what result each theory predicts, and on how the results will be interpreted before any data is collected, precisely to prevent either side from later reinterpreting ambiguous results in their own favor. In this case, the collaboration brought together the originator of integrated information theory, Giulio Tonini, together with the originator of a rival framework called Global Neuronal Workspace Theory, the cognitive neuroscientist Stanislas Dehaene, along with a large theory-neutral team of independent researchers who actually ran the experiment. Over 250 participants had their brain activity recorded using 3 different measurement techniques simultaneously: functional magnetic resonance, imaging, magnetoencephalography, in a smaller subset of patients undergoing clinical monitoring, direct recordings from electrodes placed inside the brain while they viewed simple visual stimuli. The results, published in the journal Nature in 2025, were genuinely mixed, and both original theories' proponents, to their considerable credit, publicly acknowledged that the data challenged some of their own theories' specific predictions. Rather than cleanly vindicating one theory over the other, the study found evidence consistent with some predictions of integrated information theory regarding which brain regions carry information about conscious content, while other predicted patterns of sustained, synchronized activity that the theory expected did not clearly appear in the data, and the rival global workspace theory's expectation of strong, sustained involvement of frontal brain regions in maintaining conscious perception was also not straightforwardly supported. If there is a lesson in this episode, it is a genuinely useful one for thinking about the whole subject of tonight's discussion. Consciousness science, at its most careful and rigorous, is currently a field of serious, competing, only partially supported theories tested against real data by researchers willing to have their own ideas challenged, rather than a field that has already reached a settled answer in favor of any single framework, panpsychist or otherwise. Let us shift now from neuroscience to physics, since the second major argument that gets connected to panpsychism draws on quantum mechanics, and it is an argument that requires a bit of careful, patient unpacking, because it is also one of the most widely misunderstood topics in popular science communication. Getting it right matters, since a great deal of loose talk about consciousness and quantum physics rests on a misreading of what the underlying experiments actually show. Quantum mechanics, developed in the first decades of the 20th century by physicists including Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and many others, describes the behavior of matter and energy at very small scales. And it is, by any measure, one of the most successful theories in the history of science, verified to extraordinary precision in thousands of experiments and underlying most of modern electronics. One of its central and genuinely strange features involves what happens when a quantum system, before being measured, seems to exist not in one definite state but in what is called a superposition, a mathematical combination of multiple possible states at once, each with a certain probability of being the one observed if a measurement is made. The classic demonstration of this strangeness is the double-slit experiment, first performed with light by Thomas Young in the early 1800s, long before quantum mechanics existed as a formal theory, and later repeated with individual particles such as electrons and photons in the 20th century, with results that puzzled physicists in a new and specifically quantum way. In the basic setup, particles are sent one at a time toward a barrier containing two narrow parallel slits, with a detection screen placed behind the barrier. If you block one slit and send particles through the other, they build up, over time, into a simple pattern directly behind the open slit, exactly as you would expect from tiny bullets passing through a single opening. But if you open both slits and let each particle choose freely which one to pass through, something strange happens. Instead of two simple bands of accumulated particles behind the two openings, the particles build up over many repetitions into an interference pattern, a series of alternating bright and dark bands, exactly the kind of pattern you would expect if each particle were behaving like a wave, passing through both slits simultaneously and interfering with itself, reinforcing itself in some places and cancelling itself out in others, even though each individual particle is detected on arrival as a single localized point, the way a particle should behave, not smeared out like a wave. This already tells us something deeply strange about quantum systems before we bring measurement into the story at all. The genuinely puzzling further twist, and the one most relevant to this discussion, comes when experimenters add a detector at one of the two slits, a device designed to record which slit each particle actually passes through. When this which path information is obtained, in any of a wide variety of possible ways, the interference pattern vanishes, and the particles instead build up into the simple, to-band pattern you would expect from classical particles going one way or the other. It is this specific result, that gaining which path information destroys the interference pattern, that has led to a great deal of popular science writing suggesting that observation by a conscious mind is what causes quantum systems to behave differently, as though the particles somehow know they are being watched and change their behavior out of some kind of quantum shyness. This is a genuine misreading of the physics, and it is worth explaining carefully why, since correcting it is more interesting, not less, than the popular myth. What destroys the interference pattern is not consciousness or observation in the everyday sense of a person looking at something. What destroys the interference pattern is any physical interaction that extracts which path information from the particle and correlates that information with the rest of the condiment in a way that could, in principle, be read out, whether or not any conscious being ever actually reads it out. A detector left running with its recording mechanism engaged will destroy the interference pattern, even if no human being ever looks at the recorded data. And even if the recording is deleted afterward without anyone examining it, the crucial physical process at work is called decoding, and it has been ostensibly studied and directly measured since the theoretical framework for understanding it was substantially developed in the 1970s and 80s, particularly through the work of the physicist Heinz Dieter, Zur, and later Warczek, Zurek, among others. Decoherence works, in rough outline, as follows. A quantum system in superposition can only maintain its wave-like interference behavior if it remains sufficiently isolated from its surrounding environment, meaning it is not become entangled in the specific technical quantum sense we will get to shortly, with the enormous number of particles that make up any measuring device, any stray photon, any molecule of air. The moment a quantum system interacts strongly enough with its environment to leave a durable, in principle recoverable trace of which particular state it was in, the delicate phase relationships between the different branches of the superposition are rapidly and effectively scrambled across. The vast number of environmental degrees of freedom, and the interference effects that depend on those precise phase relationships become, for all practical purposes, permanently unobservable, even though nothing in the underlying mathematics has technically collapsed anything. On some interpretations of the theory discussed below, this scrambling happens through ordinary physical interaction and ordinary physical law, with no special role for consciousness, and it happens whether or not a mind is present to register the result. A which path detector destroys interference because it is a physical system large and interconnected, enough to decohere the particles' superposition through sheer physical interaction. The same way any sufficiently large, environmentally entangled measuring apparatus does, camera, photographic plate, or Geiger counter, none of which needs to be conscious to do its job, given that decoherence provides a well-understood, thoroughly tested physical account of why superpositions appear to vanish upon measurement. Why did the idea that consciousness itself causes quantum collapse ever arise among serious physicists in the first place? And where does it stand today? The idea has a specific, traceable history. It originates most directly with the mathematician John von Neumann, who, in his rigorous 1932 formalization of quantum mechanics, pointed out that the theory, as then understood, seemed to require drawing a boundary somewhere between the quantum system being measured and the classical measuring apparatus doing the measuring, and that this boundary could, in principle, be pushed further and further along the chain of physical interaction, from the particle to the detector to the recording device, to the light entering an observer's eye, to the observer's own nervous system, without the mathematics ever telling you exactly where the boundary has to stop. Von Neumann did not himself insist that consciousness was the unique place this chain had to terminate, but he identified what came to be called the von Neumann chain, or the problem of where to place the cut between quantum and classical description. The physicist Eugene Wigner, the same Wigner mentioned earlier in connection with the effectiveness of mathematics, took this idea further in the 1960s, proposing in a widely discussed thought experiment now called Wigner's Friend that consciousness might indeed play a special role in finally resolving a superposition into a definite outcome, since Wigner found it deeply uncomfortable to imagine a friend of his performing a measurement inside a sealed laboratory, remaining in an undefined superposition of having seen one result or another from Wigner's own external point of view, until Wigner himself opened the door and looked. Wigner suggested, at least for a period in his career, that the mathematics of quantum mechanics might genuinely require a conscious observer to finally settle which outcome occurred, a view sometimes called the von Neumann-Wigner interpretation. It is important to be clear about where this idea stands in physics today, because it has had an outsized afterlife in popular culture relative to its standing among working physicists. The overwhelming majority of physicists working on the foundations of quantum mechanics today do not accept that consciousness plays any special causal role in the collapse of the wave function, largely because decoherence, developed and confirmed in extensive detail in the decades after Wigner's original proposal, provides a complete, testable, purely physical account of why superpositions become unobservable upon interaction with a sufficiently large environment, with no need to invoke consciousness at any point in the story. Wigner himself, later in his career, moved away from his earlier suggestion as decoherence theory matured. The Wigner's friend thought experiment remains genuinely useful and is still actively discussed in modern physics, including in real laboratory versions performed with photons in recent years. But its modern significance lies in what it reveals about the relationship between different observers, descriptions of the same physical situation, and about competing interpretations of quantum mechanics generally, rather than as evidence that consciousness causes collapse. This brings us to an important point that is easy to lose sight of amid the popular fascination with quantum consciousness, which is that physicists still do not agree on precisely what decoherence's success actually implies about the deeper nature of reality, even though they agree overwhelmingly on the experimentally confirmed physics of decoherence itself. Several distinct interpretations of quantum mechanics remain live options among physicists and philosophers of physics, differing not in their experimental predictions, which are identical, but in the picture of underlying reality each one offers. The Copenhagen interpretation, historically associated with Bohr and Heisenberg, generally treats the wave function as a tool for predicting probabilities of measurement outcomes without committing to a definite claim about what is happening to an unobserved system between measurements. The many worlds interpretation, first proposed by Hugh Everett III in 1957 and taken seriously by a substantial number of physicists today, proposes that every possible outcome of a quantum measurement actually occurs, each in its own separate, non-interacting branch of an ever-splitting universal wave function, so that decoherence explains why we only ever experience one branch as classical and definite, without any collapse happening at all, anywhere, ever. The pilot wave theory, originally proposed by Louis de Broglie and developed more fully by David Bohm, proposes that particles always have definite positions, guided along genuinely well-defined trajectories by an accompanying wave, with the appearance of randomness arising from our ignorance of the particle's exact initial position rather than from any fundamental indeterminism in nature. None of these interpretations, including the ones that remain seriously discussed among working physicists, require or particularly benefit from bringing consciousness into the story as a fundamental physical ingredient, and this is worth stating plainly, since it corrects one of the more persistent popular myths connecting quantum physics to mind, having cleared up the relationship between quantum measurement and consciousness. It is worth doing the same careful work with another quantum phenomenon that frequently gets pulled into panpsychist and mystical arguments, namely entanglement. Since the earlier source material we drew on for tonight's discussion described entanglement in a way that, while gesturing at something real, blurred an important distinction that is worth straightening out. Entanglement is a genuine and thoroughly confirmed feature of quantum mechanics, in which two or more particles are prepared in such a way that their properties become correlated in a manner that cannot be explained by any classical picture of the particles simply carrying predetermined, independent properties from the moment they were created. A commonly used example involves a pair of photons prepared so that their polarizations, a property describing the orientation of their oscillation, are entangled. If you measure the polarization of one photon and find it in a particular orientation, the measurement of the other photon, whenever and wherever it is eventually performed, is found to be correlated with the first result in a way that matches quantum mechanical predictions and does not match what any classical theory involving independently determined properties could produce. This last point deserves emphasis, because it is the specific content of one of the most important results in 20th century physics, a set of theoretical inequalities derived by the physicist John Stuart Bell in 1964, now called Bell's inequalities, along with the experimental tests of those inequalities carried out with steadily increasing rigor from the 1970s onward. Work that was recognized with the Nobel Prize in Physics in 2022, awarded to Aling Aspect, John Clauser, and Anton Zeilinger for their experimental contributions, closing various loopholes in these tests over several decades. What these experiments demonstrate, to a very high degree of confidence, is that no theory in which each particle independently carries a complete, predetermined set of properties, decided in advance and simply revealed by measurement, can reproduce the statistical correlations that entangled particles actually show. This is often summarized by saying that quantum mechanics is not locally realistic, meaning it cannot be that both locality, the idea that distant events cannot instantaneously influence each other, and realism, the idea that particles have definite properties independent of measurement, hold true together in the way classical physics assumed. It is precisely at this point that popular descriptions, including the one referenced earlier tonight, often slide into an overstatement, describing one entangled particle as instantaneously monitoring or communicating with its distant partner, as though information were flashing between them faster than light. This overstatement is worth correcting carefully, because the actual physics is, if anything, more subtle and more interesting than the popular version. It is provably impossible, and this has been rigorously demonstrated as a mathematical consequence of quantum mechanics itself, sometimes called the no communication theorem, to use entanglement to send any usable message or any controllable information from one location to another faster than light, or indeed faster than any signal could otherwise travel. If you only look at the measurement results obtained on one of the two entangled photons, considered entirely on its own, without any knowledge of what happened to its distant partner, those results look like a string of perfectly random outcomes, carrying no information whatsoever, exactly as they would if there were no entanglement at all. The correlation between the two distant measurement results, the fact that they match in the specific statistical pattern predicted by quantum mechanics, only becomes apparent once someone physically brings the two separate lists of results together and compares them, a process that requires ordinary, slower-than-light communication, such as a phone call or a data transfer between the two locations. Entanglement produces a correlation that cannot be explained by classical, predetermined properties, which is genuinely strange and profound. But it does not produce a channel for sending a message, and it does not involve one particle detecting or influencing the other, in any sense that allows information to move between them faster than light. Physicists sometimes describe this by saying that entanglement is a non-local correlation without non-local signaling, a precise but admittedly less catchy way of putting it than saying the particles are talking to each other across space. This distinction matters directly for tonight's central question. because a great deal of quantum consciousness speculation leans on a looser, more anthropomorphized reading of entanglement, treating it as though it demonstrates some kind of universal interconnected awareness linking distant parts of reality. The actual, rigorously confirmed physics of entanglement is stranger than ordinary intuition allows, but it is also more constrained than the popular version suggests, governed by precise mathematical rules that explicitly forbid the kind of communication a mystical reading would require. With this groundwork laid, we can look properly at the most specific and most carefully worked out proposal connecting quantum physics directly to consciousness, a theory called orchestrated objective reduction, developed jointly by the mathematical physicist Roger Penrose and the anesthesiologist Stuart Hameroff, beginning in the early 1990s. Penrose, whose broader work on the mathematics of general relativity and black holes earned him a share of the 2020 Nobel Prize in Physics, had separately argued in his books The Emperor's New Mind and Shadows of the Mind that human understanding, particularly the ability to grasp certain mathematical truths, cannot be fully captured by any computational process running on an ordinary, deterministic or algorithmic computer. Drawing on a controversial application of Kurt Gödel's incompleteness theorems to argue that human minds can, in some sense, see the truth of certain mathematical statements that no formal computational system operating by fixed rules could ever prove. From this starting point, Penrose proposed that consciousness must involve some non-computable physical process, and he suggested that this process might be found in a specific speculative extension of quantum mechanics that he had proposed on independent grounds, called objective reduction, in which the collapse of a quantum superposition is triggered not by measurement or by dicoherence, but by a fundamental instability, arising once a superposition involves a sufficient difference in the gravitational field associated with its two possible mass distributions. A genuinely novel physical hypothesis that remains untested, but that is, notably, framed by Penrose as an objective physical process requiring no observer or consciousness to trigger it. Hameroff, working as a practicing anesthesiologist, brought a specific biological candidate to this framework, proposing that the necessary quantum processes take place inside microtubules, hollow, tube-shaped protein structures found in the internal skeleton of essentially all cells, including neurons, where they play well-established roles in cell structure and in transporting materials within the cell. Hameroff had noted that general anesthetic drugs, whose precise mechanism for switching off consciousness was and remains only partially understood, seemed to act at least partly on these microtubule structures, and he proposed that microtubules might support delicate quantum superpositions of their structural configuration, with Penrose's proposed gravitationally induced collapse occurring within these microtubules on a timescale relevant to conscious experience, an event the two researchers termed orchestrated objective reduction, or ORC or for short, with each such collapse event corresponding, on their theory, to a discrete moment of conscious experience. This is a genuinely bold and specific hypothesis, and it deserves credit for being unusually concrete and, in principle, at least partially testable, compared to some of the more purely philosophical proposals discussed earlier tonight. But it has faced sustained and, according to the large majority of physicists who have examined it, largely unanswered technical criticism, most influentially from the physicist Max Tegmark, who published a detailed calculation in the year 2000 estimating how long a quantum superposition involving the relevant structures in microtubules could actually survive before being destroyed by given the warm, wet, chemically active, and highly interconnected environment inside a living neuron. Tegmark's calculation found that the relevant superpositions would decohere on a timescale of a small fraction of a trillionth of a second, many orders of magnitude too fast to plausibly play any role in neural processes, which typically unfold on a timescale of thousandths of a second or slower. This result, sometimes summarized by other physicists as the warm, wet, and noisy argument against quantum effects playing a significant role in ordinary neural computation, has been widely cited by physicists skeptical of quantum theories of consciousness. Hameroff and his collaborators have published responses arguing that Tegmark's original calculation used assumptions that do not correctly match the specific geometry and specific physical conditions proposed in the actual OR model, and that a corrected calculation, accounting for factors such as the possible shielding effects of ordered water molecules surrounding the microtubules, could extend the relevant decoherence timescale substantially by many orders of magnitude, though even these more favorable recalculations generally still fall short of unambiguously reaching the tens of milliseconds that the original theory required, leaving the dispute technically unresolved rather than settled in either direction. More recent experimental work, including some studies reporting evidence of unexpectedly long-lived quantum-like oscillations in microtubule structures under laboratory conditions, has kept the debate alive without resolving it. And no experiment to date has demonstrated that the specific gravitationally induced collapse mechanism central to Penrose's proposal actually occurs in biological tissue or indeed anywhere at all. The honest summary, consistent with how most physicists who have examined the theory in detail describe its current standing, is that orchestrated objective reduction remains a serious, carefully constructed, and so far empirically unconfirmed hypothesis, taken seriously by a small minority of researchers and viewed with considerable skepticism by the majority of physicists and neuroscientists working in adjacent fields, largely because of the decoherence timescale problem that has never been fully and controversially resolved in the theory's favor. There is one more physicist whose ideas belong in this discussion, and his proposals are, in some ways, the strangest and most genuinely mind-bending of everything we will cover tonight, precisely because they came from one of the most respected and mainstream figures in 20th century physics, rather than from someone working at the field's fringes. John Archibald Wheeler had an extraordinary career at the center of modern physics. He worked alongside Niels Bohr on early theories of nuclear fission in the 1930s, supervised the doctoral work of Richard Feynman, coined the widely used terms black hole and wormhole, and made foundational contributions to general relativity and quantum gravity across a career that spanned more than 6 decades. Late in that career, Wheeler became increasingly interested in the deep foundational puzzles of quantum mechanics, and he proposed a series of thought experiments and speculative frameworks that pushed the questions we have been discussing tonight into genuinely new territory. The most experimentally grounded of Wheeler's proposals is what he called the delayed choice experiment, first outlined in the 1970s and subsequently realized in a number of real laboratory versions from the 1980s onward, using increasingly sophisticated equipment. The basic idea extends the double-slit experiment discussed earlier with an additional twist. Wheeler asked what would happen if the experimenter's decision about which kind of measurement to perform, a decision that determines whether which path information will be available, and therefore whether an interference pattern can appear, is made and physically implemented only after each individual particle has already passed the double-slit barrier, but before it reaches the final detection screen. Naively, one might expect that the particle would have already had to commit, back when it passed through the slits, to behaving either like a wave, taking both paths at once and eventually contributing to an interference pattern, or like a particle, taking a single definite path and contributing to a simple, non-interfering pattern, since the choice about how to measure it had not yet even been made at that earlier moment, when these experiments were actually performed, using various technical arrangements involving beam splitters, mirrors, and fast-switching devices, and later using photons that had traveled significant distances, including one notable version using light from distant astronomical sources that had been traveling for many thousands of years before reaching the detector. The results consistently matched the ordinary predictions of quantum mechanics rather than any classical, common-sense expectation. The measurement outcome correlates correctly with the type of measurement eventually chosen, even when that choice is made after the particle has in an everyday sense of the word, already passed through the slits. It is important to say clearly that this does not involve sending any signal backward in time, and it does not allow anyone to change a past event in any way that could be exploited to send information into the past, a fact confirmed by the same no-communication theorem discussed earlier in connection with entanglement. What it does suggest, and this was Wheeler's central point in proposing the experiment, is that our ordinary, intuitive picture of a quantum particle having already decided, at the moment it passed through the slits, whether it behaved as a wave or a particle, independent of how it will later be measured, does not hold up. In some sense, that remains genuinely debated among physicists, the particle's history, described in the language of ordinary classical objects moving along definite paths, is not fully fixed until the measurement is completed. Even though nothing about causality in the ordinary sense, information moving backward in time, is being violated. Wheeler took this result, along with decades of thinking about the broader structure of quantum mechanics, and proposed a striking interpretive framework he called the Participatory Anthropic principle, most fully articulated in essays and interviews from the 1980s and in a frequently quoted formulation from around 2006. Wheeler suggested, somewhat poetically, that the universe, considered on the largest and most fundamental scales, should be understood not as a fixed, pre-existing stage upon which observation merely happens to occur, but as an ongoing process that is, in some genuine sense, brought into definite being through acts of observation, including observations happening now that concern events from the distant past. Since Wheeler pointed to delayed choice-type reasoning applied to light that had traveled across cosmological distances as suggesting that our present-day observations could, in a carefully qualified sense, he tried to specify, participate in giving definite character to events from billions of years ago. He summarized this with the phrase that observers are participators in bringing into being not only the near and here, but the far away and long ago. It is worth being precise about how seriously this proposal is taken within physics today, since Wheeler's genuine stature in the field has sometimes led to his more speculative, later, ideas being reported with more authority than the physics community as a whole actually grants them. The participatory anthropic principle is not a standard working part of physics in the way that, say, general relativity or the standard model of particle physics are. It is a philosophical interpretation offered by a genuinely eminent physicist of results that are themselves solidly established, namely the delayed choice experiments and the broader puzzle of quantum measurement. Many physicists who respect Wheeler's technical contributions nonetheless regard the participatory anthropic principle as an interesting but unproven interpretive gloss rather than as an established finding, and it does not carry the same evidentiary weight as, for instance, the experimentally verified predictions of quantum electricity. It sits, appropriately, alongside the other interpretations of quantum mechanics discussed earlier, competing for philosophical plausibility rather than resting on any additional experimental confirmation beyond what those other interpretations already share. Wheeler's other major speculative contribution, closely related in spirit though somewhat separate in its specific content, is an idea he summarized with the phrase "it from bit," first laid out in an influential 1990 essay. Wheeler proposed, again as a speculative framework rather than a proven theory, that the physical universe at its most fundamental level might be built not out of matter or energy as ordinarily conceived, but out of information, discrete units of yes or no answers to physical questions, from which matter, energy, and even the geometry of space-time itself might somehow be derived as higher-level, emergent phenomena. This idea, often grouped today under the broader label of digital physics or informational physics, has attracted a range of serious theoretical attention in the decades since, and it connects to some genuinely important developments in modern theoretical physics, most notably to work on the so-called holographic principle, proposed in the early 1990s by Gerard T. Hooft and developed further by Leonard Susskind, which suggests, based on careful analysis of the physics of black holes, that all the physical information contained within any region of space can, in principle, be fully encoded on a lower dimensional boundary surrounding that region, much like a hologram encodes three-dimensional information on a two-dimensional surface. This principle grew out of an earlier and thoroughly confirmed result called the Bekenstein bound, developed by the physicist Jacob Bekenstein in the 1970s, which places a strict, mathematically precise upper limit on the total amount of information that can be contained within any finite region of space, a limit determined entirely by the size of the region's boundary rather than by its volume. A genuinely surprising result with deep roots in the thermodynamics of black holes that remains one of the more secure footholds theoretical physicists have in this otherwise highly speculative territory. None of this body of work, including the holographic principle and the Bekenstein bound, which rest on considerably firmer theoretical ground than Wheeler's more speculative proposals, demonstrates that the universe is conscious, or that mind is fundamental to physical reality in the way panpsychism proposes. What this line of research does suggest, and this is a genuinely significant and still actively developing area of modern theoretical physics, is that information itself may be a more fundamental physical quantity than physicists once assumed, playing a role in the deep structure of space-time that earlier generations of physicists would not have anticipated. Whether that informational foundation has anything to do with mind, in the sense relevant to consciousness and experience, or whether it is simply a further layer of mathematical structure with no experiential character of its own, remains an entirely open question, and connecting the two, as some popular writing does with more confidence than the underlying physics currently supports, requires an additional and much less secure interpretive leap that most working physicists in this area do not make. Let us turn now to a different thread in this history, one that draws less on physics and more on the history of religion and philosophy, and that requires a bit of careful historical correction, since it is often presented with far more ancient authority than it actually possesses. The tradition known as Hermeticism traces its name to Hermes Trismegistus, meaning Hermes the thrice great, a legendary figure who was believed, in late antiquity, to be either an ancient Egyptian sage of immense wisdom, a divine or semi-divine being merging the Greek god Hermes with the Egyptian god Thoth, or in some accounts a real philosopher-priest from the distant past whose teachings had been passed down across many centuries. Under this name, a collection of Greek philosophical and religious texts, known collectively today as the Corpus Hermeticum, were composed by unknown authors, most likely in Egypt, during the first few centuries of the Common Era, drawing on a blend of Greek philosophy, particularly Platonism and Stoicism, together with Egyptian religious ideas and elements of early Jewish and Christian thought, circulating in the same intellectual environment. These texts present a cosmology in which the universe emanates from a single divine mind, sometimes called nous, and in which human beings possess a spark of this divine mind within themselves, obscured by their attachment to the material, bodily world, with the goal of philosophical and spiritual practice being to purify and awaken this inner divine spark, achieving a kind of mystical union with or return to the divine source. The Hermetic texts also include the famous formula, often rendered as that which is below is like that which is above, and that which is above is like that which is below, a statement of cosmic correspondence between different levels of reality that appears in the Emerald Tablet, a short, separate text also associated with the Hermetic tradition, whose earliest known versions actually appear not in the original Greek Hermetic corpus but in Arabic, alchemical writings from several centuries later, entering the Latin-speaking world through medieval translation. For much of the medieval period in Western Europe, the Hermetic texts were known only in fragments, but they experienced an extraordinary revival in the Italian Renaissance, when Cosimo de' Medici, the powerful banker and patron in 15th century Florence, acquired a Greek manuscript of the Corpus Hermeticum and reportedly instructed the scholar Marsilio Ficino to set aside his ongoing translation of Plato's complete works in order to translate the Hermetic texts first, believing them to be even older and even more authoritative, since Renaissance scholars, working with the limited historical knowledge available at the time, believed Hermes Trismegistus to have been a contemporary of Moses, or even older, making the Hermetic texts, in their estimation, among the most ancient religious wisdom in existence, older than Plato and perhaps even older than the earliest books of the Bible. Ficino's translation, completed and published in the 1460s, had an enormous influence on Renaissance thought, feeding directly into a broader revival of interest in Platonism, Neoplatonism, astrology, alchemy, and various forms of what scholars now broadly call Western esotericism, an intellectual and spiritual current that continued to develop across the following centuries. This historical dating and the resulting sense of Hermeticism's supreme antiquity was significantly overturned in 1614, when the classical scholar Isaac Casaubon, examining the Greek used in the Hermetic texts with the more advanced philological methods of his era, demonstrated conclusively that the language and ideas in the Corpus Hermeticum reflected the Greek of the early centuries of the Common Era, meaning the texts were written many centuries after Plato rather than before him, and that Hermes Trismegistus was almost certainly a literary invention rather than a historical author from remote antiquity. This finding, now universally accepted among historians of the ancient world, considerably deflated the Renaissance-era claims about the tradition's supreme age, though it did not prevent Hermeticism from continuing to develop and influence later esoteric, occult, and philosophical movements across the following centuries, since a text's historical age is a different question from its intellectual or spiritual value to those who continued to study it. This history matters for tonight's discussion because of a specific and, in the interest of accuracy, worth correcting detail about a particular text that circulates widely today under the Hermetic banner, and that was referenced, without full historical context, in the source material this discussion draws on. That text is a book called The Kybalion, published in 1908 under the mysterious byline 3 Initiates, and presented within its own pages as a modern restatement of an ancient body of secret Hermetic teaching, complete with quoted maxims attributed to an unnamed original source also called the Kybalion, said to preserve fragments of teaching passed down since the days of Hermes himself. Historical research conducted over the past several decades particularly by the religious studies scholar Philip Disley, has established with a high degree of confidence that the Kybalion was written entirely by a single author, an American named William Walker Atkinson, a lawyer turned publisher who was one of the most prolific and commercially successful writers within the American New Thought movement, an early 20th century spiritual and philosophical movement that emphasized the power of directed thought and mental attitude to shape health, circumstances, and personal reality, and that drew eclectically on Christian Science, various strands of popular psychology, and selectively borrowed elements of Hindu philosophy, often filtered through Atkinson's own earlier pseudonymous writings published under invented names such as Yogi Rama. Atkinson had already written extensively, under his own name and under several different pseudonyms, on very similar themes of mental power and cosmic mind well before the Kybalion appeared, and the specific Hermetic-sounding maxims quoted throughout the book, presented as ancient wisdom, do not correspond to any known passage in the genuine ancient Corpus Hermeticum or in any other verifiable historical Hermetic source. The scholarly consensus today is that the Kybalion is, in substance, an early 20th century New Thought text, dressed in the borrowed vocabulary and imagined authority of ancient Egyptian and Greek wisdom, a marketing and rhetorical choice that was, by all available evidence, a deliberate literary device on Atkinson's part rather than a genuine transmission of ancient teaching. None of this means the Kybalion lacks historical or cultural interest. It has been, by any measure, an enormously influential text within 20th and 21st century Western occult study and New Age spirituality, shaping how millions of readers have encountered ideas like the phrase, "the universe is mental," and its 7 stated principles, including the principle of mentalism it opens with. The principle that the universe as a whole is essentially mental or spiritual in nature, but describing these ideas as ancient Hermetic wisdom, without noting that the specific text presenting them in this popular form was composed in 1908 by an American occult publisher working within a documented and quite recent spiritual movement, gives the ideas a borrowed authority they have not actually earned through documented historical transmission. The genuine, ancient Hermetic texts, translated from the actual Corpus Hermeticum, do contain philosophical mentalism of their own, a real intellectual inheritance from late antique Platonism. So the broader claim that Hermeticism has historically included mind-centered metaphysics is accurate. It is specifically the popular 20th century packaging of these ideas, often mistaken by casual readers for a direct window into ancient Egyptian priestly secrets, that deserves this more careful, corrected historical placement. Having spent time with the philosophical history, the physics, and the more speculative esoteric tradition, it is worth returning to solid ground and spending a while with what mainstream neuroscience actually says about consciousness today, since this is easy to lose sight of amid the more exotic material, and it represents the area where the most genuine, steady scientific progress is actually being made, even without a final settled theory. Integrated information theory, discussed earlier, is only one of several serious frameworks currently being investigated by consciousness researchers, and it is worth introducing its most prominent rival, since the two have been repeatedly compared and tested against each other, including in the adversarial collaboration described earlier. Global workspace theory, originally proposed by the psychologist Bernard Baars in the late 1980s and substantially developed since, particularly by the cognitive neuroscientist Stanislas Dehaene and his collaborators, offers a very different picture of what makes a piece of information conscious. On this view, the brain contains many specialized processing systems working largely unconsciously and in parallel, handling vision, language, motor planning, memory retrieval, and so on. Consciousness, according to global workspace theory, arises when information from one of these specialized systems is selected and broadcast widely across a distributed network involving, in particular, regions of the prefrontal and parietal cortex, making that information globally available to many other brain systems at once for use in reasoning, verbal report, decision-making, and flexible behavior. Information that remains confined to a single specialized processing system, by contrast, can influence behavior without ever entering this global workspace, and such information, on this theory, is processed unconsciously. However sophisticated that unconscious processing might be, global workspace theory has substantial experimental support from studies using brain imaging and recording during tasks designed to compare conscious and unconscious perception, often using stimuli flashed too briefly or too faintly to be consciously reported, while still measurably influencing behavior, allowing researchers to compare brain activity between trials where the same stimulus was consciously seen versus unconsciously processed. Integrated information theory and global workspace theory differ in a specific testable way that made them well suited to the adversarial collaboration discussed earlier. Integrated information theory predicts that the neural basis of conscious content should be found primarily in a posterior, back of the brain network involving sensory and associative cortex, since this is where Tononi's framework predicts the relevant integrated causal structure is concentrated, while global workspace theory predicts a strong, necessary, sustained involvement of frontal brain regions, since broadcasting to a global workspace, on this theory, specifically requires those frontal regions to participate. As already described, the actual experimental results, published in 2025, produced a genuinely mixed picture that posed real difficulties for both theories as originally formulated. Evidence that the field's own most careful practitioners treat as a sign of a genuinely open scientific problem rather than a solved one, appropriately motivating continued research rather than premature confidence in either framework. Beyond these two prominent theories, several other serious frameworks continue to be actively developed and debated. Higher-order theories of consciousness, associated with philosophers and researchers including David Rosenthal and Hakwon Lau, propose that a mental state becomes conscious specifically when the brain generates a further, higher-order representation about that first mental state, essentially a form of the brain monitoring or representing its own processing, with consciousness arising from this act of self-representation rather than from integration or global broadcasting as such. Predictive processing frameworks, drawing on influential work by researchers including Carl Friston and popularized for general audiences by Anil Seth, propose that the brain is fundamentally a prediction machine, constantly generating internal models of the world and continuously updating them, based on the mismatch between prediction and incoming sensory data, with conscious experience, on this view, understood as something like a controlled hallucination, the brain's best current guess about the causes of its sensory input, continuously checked and corrected against reality rather than being a passive readout of the external world. It is genuinely notable and worth stating plainly as an honest summary of where the field currently stands, that none of these theories, including the two most prominent and most rigorously tested ones, has achieved anything close to full consensus among consciousness researchers, and the hard problem described at the very beginning of tonight's discussion, the question of why any of this physical processing, however precisely it is eventually mapped, should be accompanied by subjective experience at all rather than occurring in the dark, remains genuinely unresolved by any of these frameworks. Each of the leading theories offers, at best, an account of what physical conditions correlate with consciousness, or what physical conditions seem necessary for it, which is valuable and testable, and has produced real clinical tools like the perturbational complexity index described earlier. None of them, on the honest assessment of most philosophers working closely with this material, including committed physicalists among them, currently offers a fully satisfying explanation of why those physical conditions should be accompanied by any inner experience whatsoever, as opposed to simply being complex information processing occurring without any subject present to experience it. This gap between correlation and explanation is precisely the space in which panpsychism and its various philosophical rivals continue to find room to operate as live, unresolved options rather than settled conclusions. It is also worth noting that consciousness research today extends well beyond adult human waking experience into a genuinely fascinating range of altered and unusual states that offer additional clues. Even without resolving the deeper theoretical questions, researchers studying dreaming have found that certain brain regions, particularly a posterior, back of the brain area, sometimes called the posterior cortical hot zone, show activity patterns that track the presence or absence of dream experience during sleep with notable reliability, adding empirical weight to theories, including integrated information theory, that emphasize posterior brain regions in generating conscious content. Researchers studying anesthesia have used tools like the perturbational complexity index to track, in careful controlled studies, exactly how and when consciousness fades as anesthetic drugs take effect and returns as they wear off, revealing that the loss of consciousness under most common anesthetic agents corresponds specifically to a breakdown in the brain's capacity for the kind of integrated, differentiated activity these theories emphasize, rather than simply to an overall reduction in brain activity levels. Since a brain under anesthesia can remain quite active in a purely energetic sense while losing the specific complex, integrated pattern of activity associated with conscious awareness, researchers studying meditation, using long-term practitioners as research subjects, have documented measurable, reproducible changes in brain structure and function associated with different types of contemplative practice, offering another angle on how conscious experience relates to underlying neural organization, though interpreting exactly what these changes reveal about the fundamental nature of consciousness itself remains, like everything else in this field, a matter of active, ongoing interpretation rather than settled fact. Before closing, it is worth addressing one more claim that often appears in popular treatments of this subject: the suggestion that the large-scale organization of galaxies across the universe, the fact that they are not scattered randomly but instead cluster together in vast filaments and sheets separated by enormous, comparatively empty voids, is itself a sign of some guiding cosmic intelligence at work, arranging matter into patterns too orderly to be accidental. This is a claim that can be checked against what cosmologists actually understand about how large-scale structure forms, and the honest answer is that this organization, while genuinely beautiful and genuinely worth marveling at, is well explained by ordinary physical processes that have been modeled with considerable success and tested against detailed observations. The universe's large-scale structure, often called the cosmic web, traces its origin back to extremely small, essentially random fluctuations in the density of matter present in the very early universe, fluctuations that have been directly measured with remarkable precision in the faint, ancient glow of light called the cosmic microwave background, radiation that has been traveling toward us since the universe was only a few 100,000 years old. These early fluctuations were tiny, differing from the average density of the early universe by only a small fraction of a %, but they were enough, and gravity did the rest. Regions that started out very slightly denser than average exerted very slightly stronger gravitational pull, drawing in a little more surrounding matter over time, which made them a little denser still, and pulled in even more matter, a self-reinforcing process that, given the roughly 13 billion years since, has grown these initially tiny fluctuations into the dramatic filaments, clusters, and voids astronomers observe today. Detailed computer simulations that begin only with these small, measured initial fluctuations and the known laws of gravity run forward across simulated cosmic time, reproduce the observed large-scale structure of the real universe with impressive accuracy, matching the sizes, shapes, and statistical distribution of galaxy clusters and cosmic voids found in large astronomical surveys, an essential ingredient in these simulations, and a major reason structure formed as efficiently and as early as it did. Is dark matter a form of matter that does not emit, absorb, or reflect light, and that has so far only been detected through its gravitational effects? But that appears, according to multiple independent lines of evidence, including the rotation speeds of galaxies, the bending of light around galaxy clusters, and the detailed pattern of fluctuations in the cosmic microwave background, to make up roughly 5 times more of the universe's total matter content than the ordinary atomic matter that makes up stars, planets, and living things. Because dark matter does not interact with light or with ordinary matter through electromagnetic forces, only through gravity, it was able to begin clumping together under its own gravitational attraction earlier and more efficiently than ordinary matter could, forming a kind of gravitational scaffolding of unseen material that ordinary atomic gas and dust later fell into and collected around, eventually igniting into the first stars and galaxies. This scaffolding explains, in considerable and well-tested quantitative detail, why matter in the universe today is arranged the way it is, clustered along filaments and sheets that trace the underlying distribution of dark matter, with vast, relatively empty voids in between, where the initial density was very slightly below average and matter was correspondingly drawn away rather than toward. None of this requires or benefits from positing any guiding intelligence directing the process. Gravity, acting on initial conditions that were themselves the product of quantum fluctuations, stretched to cosmic scales during an early period of extremely rapid expansion called inflation, is, according to the detailed and repeatedly tested consensus model of cosmology, sufficient to explain the cosmic web's structure without additional ingredients, beyond the ordinary laws of physics operating over enormous stretches of time. This does not mean the structure is any less remarkable to contemplate. There is something genuinely moving about the fact that the same simple, gravitational law that keeps your feet on the ground and holds the moon in its orbit, given enough time and enough starting material, naturally organizes matter across unimaginable distances into structures that echo, at a vastly larger scale, the branching patterns you might see in a river system, or the patterns of neurons in a brain, or the veins of a leaf, patterns that arise in every one of these very different physical systems, from comparatively simple underlying rules playing out over time and space, without needing to postulate a shared underlying consciousness to explain why comparable branching, filamentary patterns show up again and again across such different scales of nature. This kind of recurring pattern across different physical systems is itself an active and genuinely interesting area of research within the mathematics of complex systems, sometimes discussed under the heading of universality, but it points toward shared, comparatively simple underlying mathematical principles governing how networks and branching structures form under a wide range of physical constraints, rather than toward any evidence of a guiding cosmic mind. It is a good example of how something can be genuinely awe-inspiring, worth the wonder people naturally feel looking at images of the cosmic web, without needing consciousness, purpose, or intention to be built into its explanation. So where does all of this actually leave us? After this long, unhurried walk through philosophy, physics, and neuroscience, it leaves us honestly without a settled answer. And it is worth sitting with that unresolved feeling for a moment, rather than rushing past it. Because an honest uncertainty, carefully mapped, is a genuinely valuable thing to hold, quite different from simply not knowing where to look at all. What we can say with confidence is this: consciousness remains one of the genuinely open problems in contemporary science and philosophy, not because researchers have been careless or unimaginative, but because the problem itself, the question of why physical processes should be accompanied by subjective experience at all, resists every method that has so far been tried against it. We can say with confidence that integrated information theory has produced at least one genuinely useful clinical tool, the Perturbational Complexity Index, now used in real hospitals to help detect covert consciousness in patients who cannot otherwise communicate, a rare and valuable case of abstract theorizing about the deepest nature of mind translating into something that has already helped real people. We can say with confidence that the broader, more panpsychist adjacent implications of integrated information theory remain genuinely contested within the scientific community, contested enough that a large group of respected researchers were moved to publicly challenge the theory's standing in 2023, and contested enough that a rigorous, carefully designed adversarial test in 2025 produced a result that satisfied no one completely, which is precisely the kind of outcome careful science should be willing to accept and learn from. Rather than the tidy resolution a documentary script might be tempted to manufacture, we can say with confidence that quantum mechanics, despite decades of popular writing suggesting otherwise, does not currently require or particularly support the idea that consciousness plays a special causal role in physical reality, since dicoherence provides a thoroughly tested, purely physical account of why quantum superpositions become unobservable upon interaction with a large environment, with no need for an observing mind anywhere in the story. We can say with confidence that quantum theories specifically proposing consciousness as a physical phenomenon located in brain microtubules remain a minority position among physicists, held back by a serious and so far unresolved objection concerning how quickly quantum coherence should be destroyed inside the warm, chemically busy environment of a living cell. And we can say with confidence that some of the material commonly presented as ancient, mystical wisdom pointing toward a conscious universe, particularly the specific and enormously popular text called the Kabbalion, turns out, on careful historical examination, to be a comparatively recent invention, composed by an early 20th century American writer working within a documented, traceable spiritual movement, its claimed ancient origin a literary device rather than a historical fact. None of this settles the deeper philosophical question that started us off tonight, and it would be dishonest to pretend that it does. Serious, careful philosophers, including some with no religious or mystical commitments whatsoever, continue to find the case for some form of panpsychism genuinely compelling, precisely because the alternative positions, strict physicalism, substance dualism, and illusionism, each carry their own significant unresolved difficulties, and because the argument that experience is real, and that a universe fundamentally without any trace of it seems mysterious to imagine ever producing it from nothing, remains, on its own terms, difficult to simply wave away. Other equally serious philosophers find the combination problem, the puzzle of how countless tiny sparks of basic experience could ever merge into the single, unified experience of an actual mind, decisive enough to rule panpsychism out as currently formulated, at least until someone offers a considerably more developed answer to that specific difficulty than currently exists. Research continues actively on several fronts, and it is worth knowing, in broad terms, where scientists and philosophers are currently looking for further clues. Neuroscientists continue refining large-scale, high-resolution recordings of brain activity, hoping that direct observation of increasingly fine-grained neural dynamics across increasingly large populations of neurons recorded simultaneously will eventually distinguish more clearly between the competing theoretical frameworks discussed tonight, building on the kind of careful adversarial testing pioneered by the Cogitate Consortium. Physicists continue developing and refining tests of quantum coherence in biological and near-biological systems, following up on the ongoing dispute between Tegmark's decoherence calculations and Hameroff's proposed refinements, with better laboratory tools for directly measuring quantum coherence times in complex molecular structures becoming available as quantum sensing technology continues to improve. Technology originally developed for entirely different practical purposes such as quantum computing and precision measurement. Philosophers continue working on the combination problem and on alternative formulations of panpsychism, including cosmopsychist proposals that start from a single, unified cosmic consciousness and try to explain individual minds as a kind of differentiation or partition of that larger whole, rather than starting from countless separate micro-experiences and trying to explain how they combine upward. And clinicians continue expanding the practical use of tools like the Perturbational Complexity Index, extending careful, theory-grounded methods for detecting consciousness into new patient populations and new clinical contexts. Work that will keep generating real, useful data regardless of how the deeper theoretical debates eventually resolve. It is worth ending, as promised at the start, without manufacturing a false sense of resolution or a dramatic final reveal, because the honest state of this subject does not offer one, and pretending otherwise would do a disservice to just how genuinely interesting the unresolved version of the story actually is. What we are left with, after all this careful walking through history and theory and evidence, is something quieter and, in its own way, more durable than a tidy answer. We are left with the plain fact that you are, right now, having an experience, that this experience is undeniably real to you, even though no one has yet explained, to everyone's satisfaction, why it exists at all. And that some of the most careful, rigorous thinkers across many centuries and many disciplines have looked hard at this same plain fact and found themselves, again and again, drawn toward the possibility that mind might be woven more deeply into the fabric of things than a simple picture of dead matter and late arriving thought would suggest. That possibility remains unproven. It also remains, after a great deal of serious scrutiny from serious people, entirely undismissed. Perhaps that is simply where an honest mind, looking closely enough at its own strange and undeniable existence, is bound to end up for now, somewhere between certainty and dismissal, comfortable enough with not knowing to keep looking without needing to have already arrived, and that, more than any conclusion, might be the most restful place to leave it as you drift off tonight.